Hello, lovely people. What is up? Today we are solving Leetcode problem number 110, balanced binary tree. So before we dive into this question, let us take a look at what is binary tree and try to understand it. So visualize this. In a family tree, we have a grandparent. They have children, and those children have children, and so on. That structure is a tree. A tree in data structures is a way to organize data in levels. One piece of data connects to other pieces like branches. There are no circles or cycles, no going backwards, just top to down flow. So any trees in data structure actually looks like a real tree that is upside down. So the root is on top and the nodes are the leaves that are below. So binary trees. What is binary? It means true. So binary tree simply means every node can have at most two children, not more than two. Only left child and right child. That is all. So when you take a look at this example, each number is a node and each line is a connection. No node here has more than two children. So this is a perfect example of a binary tree. So there are a few tree terminologies that we need to keep in mind while solving such problems. The first one is root. Root is the topmost node. It's like the boss. And then the parent. A node that has children is called a parent node. And then comes child. A node coming from a parent is called a child node. And then leaf. A node without any children. A node that has no children branching out from it. It's the end of a branch. It's called a leaf node. And then height. Height measures how tall a tree is. So why do we even use trees? Because trees make searching faster and sorting easier. So for example, in your computer, the folder structure, and in your books, the table of contents, and any decision that you make in a game, all are made by trees. So to sum it all up, a binary tree is a structure where each item can point to at most two other items, left and right. Now, let us go back to the question and take a look at it. So, they have given us a binary tree and asked us to determine if its height is balanced. Okay, now let's take a step back and understand what is a height balanced binary tree. So, if you remember, height is how tall the tree is. If the height is higher, that is, the tree is tall, the computation becomes slow. So, we prefer short, compact trees. A binary tree is height balanced if for every node, the height difference between its left and right subtree is at most 1. So if you can see in the given example, the difference between the right subtree and the left subtree 2 minus 1 is 1. So this is a balanced binary tree. Now if you take a look at the second example, the depth of the left subtree is 1, 2, 3 and the right subtree's depth is 1. 3 minus 1 is 2. So this is not a balanced subtree. So we return false. So here the intuition is, instead of checking balance first and then computing height later, we combine both and do it at the same time. So every recursive cell returns the height of a subtree and checks balance along the way. This is why we should use post-order DFS. So what is post-order DFS traversal? So we cannot know the height of a node until we know the height of its left and right children. So we always go from bottom to top. If we use post-order traversal, we visit every node of the tree in this exact order. Left subtree, right subtree and the root node. This is the post-order traversal. Like in this example, first we visit 4, then the other 4, then its parent node 3, and the right subtree 3, and then its parent node 2, and then its right subtree 2, and then the root node 1. This is post order traversal. So how are we going to use it? For every node, we get the height of left subtree and get the height of right subtree, and if left minus right is greater than 1, the tree is not balanced. So we return the height, which will be 1 plus maximum of left or right. That is all. So in this particular example, if we take a look at the leaf nodes, the depth is 1 because there is no other subtree, and in the rightmost leaf node, the depth is 1 because here also there is no subtrees. So it will be 1 minus 1, which will be 0. So for the next step, we take 1 and 1, add it and assign it to the parent node, which will be 2. And then we visit its adjacent right subtree, and here we keep the depth as 1 plus maximum of left and right. Maximum of left and right is 0, plus 1 is 1. Here also 2 minus 1 is 1, which is still balanced. Now moving up, the left subtree will be assigned a value of 3 because maximum between 2 and 1 is 2, plus 1 is 3. And then when we go to the right subtree, it will be 1 because there are no subtrees. Then if we try and find the difference between that, we get the value as 2, which states that our given tree is not balanced. So now let us take a look at the code. So first we define a DFS function with an attribute node, and if it is not a node, return 0. And then we state left is equal to DFS of node of left. So this particular line means go to the left child node. Then we check if left is minus 1. If it is minus 1, we return minus 1. And then same we are doing with the right. We are moving to the right subtree, and then if right is equal to minus 1, we return minus 1. And then to check the balance condition, we see if the absolute value of left minus right is greater than 1. If it is, we return minus 1. And then we return 1 plus maximum of left and right. And then finally, we use this DFS function and return DFS of root is not equal to minus 1. This will return true or false according to the test cases. Now let us run this code. So yeah, as you can see, the code is running in the most optimal time. So that's all for today. Hope you guys enjoyed today's video. See you in the next one. Bye bye.